So good morning, everyone. My name is Sikandar Ali, and today I'm going to present my work, which was automation of mid-infrared spectroscopy setup for the transient absorption measurements. This work was done at the Liberty Hubert Curian, very next door, and it was under the supervision of Dr. Vincenzo Di Michel. So what was the motivation behind our work? As we know that in physics and chemistry, the fundamental processes, they happen at the femtosecond to nanosecond scale. And to study these kind of processes, we can use the mid-infrared spectroscopy. As we know that the vibration of the molecules lies in the range of the mid-infrared light. So, but the problem is that if we do it or study it manually, it can cause the errors or it lack the repeatability, and also the system or the setup will be very slow. So what is the solution? The solution was the automation of the process or automation of the setup for the experiment, and that was the motivation behind our work. So what is the pump and probe spectroscopy technique, how they do it, and how we can create the molecular movie, the dynamics of the molecules. So what happens is that they use two type of the beams. The one is the pump beam and the one is the probe beam. What happens is the intense pump beam excites the molecules, and it excites the molecule in the excited state. And after a control time delay, a probe beam comes and measures what are the changes caused by the pump beam in the sample. So after scanning through the different optical delays between the pump and the probe, we can create the movie of the dynamics of the molecule, that how it behaves after it gets excited. The basic or the fundamental signal that we measure in the transient absorption spectroscopy is actually, the change in the absorption of the material or the sample when it gets excited. So here you can see that if I'm here you can see that in the formula, the system, the IX shows when the system is in excited state, or the IGR is when the sample is in the ground state. So we differentiate how the sample behaves after it gets excited. And the basic signals or the basic components that contribute towards the detection of the signal are ground state bleaching, stimulated emission, and excited state absorption. In the ground state bleaching, what happens is that our pump excites the sample or bleaches the ground state, and that's why we get the negative signal. And in the stimulated emission, our probe beam actually stimulates the excited sample, and it increases the intensity that we measure in the excited state. It also creates a negative signal. And in the excited state absorption, the already excited sample absorbs our probe beam. So the detected intensity becomes low, and it gives us the positive signal. This is the experimental setup that we used during our work. There are two paths. One path is for the probe beam and one path is for the pump beam. We use the femtosecond laser, and most of the power goes into the path of the probe beam because it was used to generate the mid-infrared light using the optical parametric amplifier, which uses the non-linear phenomena, and it requires a very huge amount of energy. So during our work, we worked on the automation of optical chopper, spectrometer, and the optical delay line using the Python script. What was the challenge during our detection? We know that the fundamental or the standard silicon cameras that we use in the laboratories, they are blind to the infrared light. So what we did it, we used the up-conversion technologies. We converted our infrared signal into the near infrared or the visible range, and it was then detected by our spectrometer and camera, which was Octoplus camera. To validate our script in the real time, our motivation or our aim was to create the zero baseline using our script. And for that, we use only one beam. And the raw spectrum of the beam that we use is shown in the left figure. And it was you can see from the figure, it was around the pixel 800 to 1300, and that was the output that we got. But there was a little challenge that this baseline was drifted from the zero, which was due to the laser fluctuation or detector noise. And to validate our results, what we did it, we saved the multiple datas in the offline mode using the internal trigger mode, in which the detector actually triggers the measurement, and also the external trigger mode through which our laser was triggering the measurement, and we got the similar results, which validates our script. And to precisely control the time delay between our pump and probe, we use the motorized stage, and we use the second harmonic generation and cause correlation technique to find the reference or zero time delay between the pump and probe. And the zero time that we found was at 14.5 millimeter. And using this reference 0 point and our script, we targeted the different positions to move our delay line, and the difference or the position error that we got was under 0.1 micrometer, which was very good result. And to differentiate between the excited state signal and the unexcited state signal, we use the power meter and the photodiode sensor, and using the beam through the optical chopper and our script, by measuring or by selecting a threshold power, we were able to differentiate between the excited and the unexcited state signal. This was the digital signal that we generated with our script, and here one represent the excited signal and the 0 represent the unexcited signal. In conclusion, we automate our system. We identified the challenges that we found during our work, and this work laid the foundation for a complete, robust, automated, time-resolved spectroscopy experiment in the future. And in the end, I would like to thank Manutech-SLEIGHT for giving me opportunity to speak up, and thank you.
Thank you. So I'm waiting for questions. Still no question? So I have a question, if you want. So you are talking about a Python script.
Yes.
And I was wondering, can you put the slide where there is a setup?
Where is the setup? Yes, yes.
Yes. Yeah.
Yes.
No.
Sorry.
Yes. Yes. Here. So, so the Python script, are they processing some data that are
yes.
stored during the experiment?
Yes.
Is there any real-time processing during the setup?
The Python script were actually for the spectrometer, optical delay line, and optical chopper. The spectrometer, the Python script that we use for the spectrometer, it was actually to measure the signal during the experiment, which was the transient absorption signal, which is actually the difference between the absorption of our sample when it is excited or when it is not excited. That was the transient absorption signal measured by our script. And the other Python script that we use, it was to control the delay line during the experiment. We know that we have to scan, or to create the movie of the molecular dynamics, we have to scan the delay line, that how the molecule is getting de-excited after it gets excited. So we scan at different time delays between our pump and probe. So it was the real time. It was the real time.
So the Python script help you to tune your...
Yes, yes.
Okay, thank you. Okay, nice. So is there any question? No. Okay, thank you again.